Hello everyone, welcome back to the course on VLSI Physical Design. So today we are going to cover a new topic which is obviously related to digital ASIC design. That is, this one is also an important, that means chapter which you need to be covered, that is static timing analysis. So that means in the last few class we have seen that how to start with design compiler, then what are the commands are available, that means how to give the area constant, how to give the power constant, how to give this timing constant, all those things in design compiler that we have seen. So now again when after that means generating the netlist file using design compiler, so now that netlist file I will use for the further proceedings of digital ASIC design. So that means after creating the netlist file, what is there? That means we need to do the timing analysis. So why static timing analysis is very much important in digital ASIC design, that we will cover now, and after this presentation we will see, that means how to work with, actually we will use Synopsys PrimeTime toolset for doing this static timing analysis. That means here actually in design compiler also we have done the timing analysis, okay, but that is at that time I said that is the rough estimation, but here we will calculate this timing and information about the chip very accurately. Okay, so before that a basic, that means brief about this, what is static timing analysis, what are there, that means how you can calculate, what are the fundamentals of this, that we will see, and what are the commands associated with that we will see, and then we will see the demo on that. So first, what is static timing analysis? Static timing analysis is a method of validating the timing performance of a design by checking all possible paths from timing violation under worst case conditions. It considers the worst possible delay through each logical element, but not the logical operation of the circuit. It means, that means why I need this static timing analysis is that for all worst case condition, that means if there is any kind of violation, so whenever we are designing a complex chip, at that time each and every path, there might be millions of paths or millions of nets are there. So whether for each of the nets or each of the paths, whether the timing information or the timing, that means requirement, that is meeting or not, that we have to check very carefully. So that's why we do static timing analysis. That means so whether we actually have to make it confirm that okay, there is no violation. After that we can proceed to the further of this design procedure, which is the physical design part. So in comparison to the circuit simulation, static timing analysis is faster and more thorough. Okay. So circuit simulation means actually what we can do, that is different aspects of that, and simulation is different. We can do that means functional simulation, we can do logical simulation, we can do circuit simulation. So simulation is a different aspects of that, but here we are doing the timing analysis, only calculating the timing information of each of the nets and each of the gates. Then we are calculating the corresponding that means time information under worst case condition. We are not considering best case condition here. So to start with that means static timing analysis, two important factors you have to know, that is setup time and hold time. So what is setup time and what is hold time? Setup time indicates the time before the clock edge during which the data should be valid or the data should be stable. That means it should be stable during this period and it should not be changed. Any change during this period would trigger a setup time violation. Setup time means before the clock edge occurs, the data must be stable. The data, that means stable means it will not change its position, whether that is 0 to 1 or 1 to 0. So if it is happens, then you will get the violation. So why I need, then that means need to do that, just like that means the data whenever the clock edge occurs, so at that time the data is basically fed to the corresponding flip-flops. So the data, if the data is changed, so it needs some time to recognize what is the value in the data. So that's why to recognizing that value I need some time. So before the clock edge occurs, so what time is required, that is known as setup time, whereas after the clock edge occurs, what time I require to properly recognize, okay, the value is 0 or the value is 1. So to recognize that value, what time is required, that is known as hold time. So hold time, actually theoretically the definition of hold time is it indicates the time after the clock edge during which the data should be held valid. That means the data will not change and it will remain stable. So if any change occurs, obviously the flip-flop will go to a, that means it cannot recognize the data properly, so you will get a metastable state. So that's why you will get the hold time violation. Okay. So this is one of the example. So that means whenever this clock edge occurs, so before the, you see here, that means, so you see here this portion is basically here, basically in this line, this is the setup time. So before the clock edge, this is the clock edge is happening here. So before this clock edge, what time is required for where the data is not changed? So this time is basically known as the setup time. So here the setup time value is 2 nanosecond. So what is hold time? So hold time is that, suppose here this clock edge occurs. So after the clock edge occurs, what time I require, not me, the flip-flop requires for recognize the data properly, this time is known as hold time. Okay. So here you see that hold time is greater than 1 nanosecond for this purpose, for this example. So and based on this setup time and hold time, we basically calculate what will be the operating frequency of my circuit. So there are some equations to calculate what will be the timing in, that means requirement for each of the clock, that means paths, or each of the, that means where the clock edge basically appears. So suppose you are getting this timing violation, that means you are getting hold time violation or you are getting setup time violation. So at that time, how you will remove those violations, how you will fix those problems, how you will, that means fix those timing violation. So there are several ways to do that. So one of that way is optimization using synthesis tool. So if you optimize the path, suppose one path is basically it is taking too much of time. So that's why you are getting the corresponding setup time violation or hold time violation. So at that time, using the synthesis tool itself, if you optimize those paths, so obviously you can fix the violation. So here it says that this is the easiest way of all the other operation. Few of the techniques have been discussed in section optimization technique, that means before. So few other techniques will be dealt with later in this following lecture. Then microarchitectural tweaks. Microarchitectural tweaks means, so you as microarchitectural tweaks means, so in the last few class we have seen that how we can do this resource sharing, how we can do that common sub-expression elimination algorithm. So something like this. So these are the architectural tweaks we use to reduce or for optimizing the circuit. That means basically we are intending to increase the performance of my circuit. Okay. So this you can use for reducing the timing violation. So microarchitectural tweaks is a manual approach compared to the previous one. That means compared to the previous one means optimization which we can do through synthesis tool. So this is a manual approach, not the automated approach. So here the designers should modify the code to make microarchitectural changes that affect the timing of the design. So again we have already discussed this, I think in the last few class. So then architectural changes. Architectural changes means, this is microarchitectural changes. Then architectural changes. Architectural changes means, suppose for one multiplier design or for one adder design, there are several adder design like carry save adder, carry skip adder, carry lookup adder, ripple carry adder. So there are several adders are available, that means different architecture, though it is doing the same operation wise it is same, it is doing the addition, but there are several architectures are available. Among them, some of them are, that means timing wise they are fast, some of them are area wise they are taking low area, some of them are like low power. So each of the, that means these adders have different property. Basically they have been designed, the architecture has been, that means made in such a way so that it can gain that means gain the benefit in terms of speed, power or area. Okay. So that's why you can change if it is violating, so at that time you can change the architecture so that the corresponding requirement that met and you will not get the violation at that time. Okay. So there are so much of this, that means optimization, that means architectural changes you can do. So optimization using synthesis tool, what you can do, compilation with compile, that means ultra or map effort high option, group critical paths together and give them a weight factor. That means you can do grouping and ungrouping in design vision, that we have seen already. So then register balancing or register retiming you can say, choose a specific implementation for a module, then balancing heavy loading, that means for high fan out, that means need you can balance the load. So this is, that means how you can do this compilation with map effort high, we have already said, that means see these things, register retiming and then group critical path, with that all these things we have seen. So then as I said that means you can choose different kind of architecture for adder implementation. Okay. So whenever we are using these Designware libraries, so at that time what I said, if I use plus, so it will take addition, if I that means the assign star, so at that time it will take multiplier. So now here you can, that means mention that which architecture you want to choose, that option is also there. How you can choose? You can mention that minus RPL, it indicates that okay, you choose the architecture as ripple carry adder, minus CLA, okay, this is carry look ahead adder, minus this CLF, so fast carry look ahead adder. So that means now you can choose that what type of architecture you need whenever you are doing the synthesis automatically. So at that time you choose what type of library, that means what type of component you need from the library. So based on that the architecture will be selected, and it will be, whenever in this compilation, that means whenever there will be the translation from the generic netlist file to the corresponding target library, so at that time it will be done or it will be mapped onto using that particular architecture, right. So then micro architectural tweaks, how you can do, you can use this logic duplication to generate independent these paths, then balancing of logic between these flip flops, then priority decoder you can use instead of multiplexers, and again you can use this logic duplication for independent to generate independent paths. Okay. So these are the micro architectural tweaks you can use. So how we can do this register balancing? Register balancing, how you can do, that means how you can balance the logic between two flip flops. So this is actually there one term is there, that is clock domain crossing. So this clock domain crossing here, as we are using only a single clock, so at that time it is very much easier. Suppose two, that means registers are there, one is driven by clock 1 source and this another clock is driven by clock 2 source, and in between of them there is this combinatorial circuit. So to synchronize these two particular flip flop, it is very much complicated. So you need to know, or you need much knowledge to how to balance or how to synchronize these two particular flip flops which is running on two different clock, so that that means you don't get any kind of violation, that is whether that is setup time violation or hold time violation. So we are not covering that clock domain crossing here. Okay, so but if you are interested, you can Google it and you can go to that clock domain crossing. So basically clock domain crossing is the important factor in digital ASIC design. So here actually balancing of logic between flip-flops, how you can do. So you can just write this balance underscore register command in the Design Vision or in the PrimeTime tool, so that automatically whatever is that means missing, that automatically it will be done by the tool itself in the automated way. So then after that, so all these things what we said, that is related to setup time violation. Now if you are getting hold time violation, so at that time how will fix the hold time violation? Okay, so hold time violation means you are getting, that means your data arrival time is more than it is required, right? So at the time hold time violation, in hold time violation you will get whenever your clock is basically appearing later than your data has already arrived. Okay, so at that time you will get that kind of hold time violation. So hold time violation occur when the signal arrive too fast, causing them to change before they are read in by the device or by the flip-flops or the registers. That means here clock is basically appearing more late than the data is arrived. So the best method to fix the hold time violation is to add buffers on those paths. So that means you can add the buffers on the particular clock path, so that the clock will arrive little bit later, as the data has already arrived. So I have to, that means synchronize that, okay, the clock will be arrived little bit fast, that means later, so that I can fix the corresponding hold time violation. So the buffers generated additional delay, slowing the path considerably, and one has to careful while fixing the hold time violations. Too many buffers would slow down the signal a lot and may result in setup violation, which obviously a problem again. Okay, so what is your requirement? Based on the requirement only, you have to put the number of buffers on that particular clock paths or on that particular paths which are having that fixed hold time violation, whether that is clock path or any other path. So then why this timing analysis is important when you are designing a chip? Timing is important because just designing the chip is not enough. We need to know how fast the chip is going to run and how fast the chip is going to interact with the other chips, how fast the input reaches to the output, etc., etc. Timing analysis is a method of verifying the timing performance of a design by checking for all possible timing violation in all possible paths. That means if there are several paths, so for several paths, how each of the paths this timing information is, that means what are the values that you need to find out using, and that you can do only by that means doing this static timing analysis only. Then my question, that you may ask the question that why I need to know this static timing analysis, why it is not dynamic timing analysis, what is the difference between them? So timing analysis can be done in both ways, static as well as dynamic, but dynamic timing analysis requires a comprehensive set of input vectors to check the timing characteristic of the paths in the design. That means dynamic, when I can say, when I can put some real-time test vectors or real-time data to the design, and then I can check that okay, for this particular set of signals, how the data or what is the timing requirement for my design. So on that dynamic environment, I can do the dynamic timing analysis. But here, whenever we are developing the chip, so at that time, how I can apply the real-time test vectors to the corresponding circuit. So that's why this dynamic timing analysis at that time we cannot do. Though we can do by using some that means generating the test vectors, and then we can apply, and then we can do. We also do the dynamic timing analysis, but the static timing analysis is used more than that dynamic timing analysis. Basically, it determines the full behavior of the circuit for a given set of input vectors. Dynamic simulation can verify the functionality of the design as well as timing requirements. For example, if we have 100 inputs, then we need to do 2 to the power of 100 simulation to complete the analysis. Why 2 to the power of 2? Because each of the, that means signals or each of the inputs, it can contain either 0 or 1. So that means for 100 inputs, it will be a 2 to the power, that means 100 number of, that means test vectors I have to put. Okay. So that's why this amount of analysis is astronomically compared to the static timing analysis. So that's why, that means the cost of or the, that means the requirement for doing this dynamic timing analysis is very much complex. There, but in compared to dynamic that means timing analysis, static timing analysis checks every path in the design for timing violation without checking the functionality of the design. This way, one can do the timing and functional analysis same time but separately. This is faster than the dynamic timing analysis because there is no need to generate any kind of test vectors. That's why STA is the most popular way of doing the timing analysis. That means here we are not applying. So that means dynamic timing analysis is more similar to the functional simulation. That means in functional simulation, what we do? We put some of the test vectors and then we see how that means how my design is basically performing and what is the behavior of my design. So here in static timing analysis, we are not putting any test vector. We are just calculating, that means what is the start point, what is the end point. So based on that, and how many gates, how many nets it is passing through. So based on that, we calculate it, what is the timing information for that particular path, whether that is 0 or 1. So then there are few actually terminology which are basically associated whenever we are calculating the timing information. So there, one of them are like a false path. So during the last lectures, we have talked about that. We have seen this false path and multi-cycle path. So what is that false path? If any path does not affect the output and does not contribute to the delay of the circuit, then that path is called as false path. That means that path is there, but it is not coming into the picture of input to the output. So critical paths comes, that means when? That means whenever there is a input to the output connection. Okay. But if any path is there, but it does not affect the output, okay, and does not contribute to the delay of the whole circuit. Delay of the whole circuit means the paths which are related to delay of the circuit, how we can calculate? We can calculate based on the input, the time taken for the input applied to the output I am getting. How much time it is taking to do that job. So that is the basically timing requirement of my circuit. So if one path is there that is not coming into the picture of that, so that path will be known as false path. So multi-cycle path, what is multi-cycle path? Multi-cycle paths in a design are the paths that require more than one clock cycle. So that means some paths it require more than one clock cycles. So we will see the examples, so at that time it will be much more clear to you. So therefore the require special multi-cycle, they require special multi-cycle setup and hold time calculation. Then mean and max path, the paths must match a delay constant that matches a specific value. It is not an integer like the multi-cycle path. For example, delay from one point to another point, the max will be 1.67, minimum will be 1.87 nanosecond. That means why this, that means then disable timing arcs. Disable timing arcs means, suppose for a gate I have 3 input, that is A, B and C, and the output is out. Now I want to stop the affecting the input A to the output. So how can I do that? I can, that means I can disable the timing path from A to the output. That I can do, so that it will not come into the picture while calculating the timing information for that particular gate. Okay, that we can do. So that means whenever we are doing a calculation, that means for a bigger circuit, so at that time one path I can disable so that it cannot affect the corresponding timing, whole timing requirement of the circuit. So then setting up constant to calculate the timing. So we have to calculate the constant. So yesterday whenever we are doing this working on the design compiler, so at that time what we have seen, we have set a initial, that means arbitrarily we have set a value for the clock period. Then we see what is the timing requirement, what is the values of slack, okay, so that we have seen. So then after that we can see that okay, the data arrival time is much more than the actual one, which is actually required. So at that time, based on that, I can reduce the clock period. Then after that again we will compile, and then we will see that okay, the slack is positive or negative. If slack is negative, at that time again I have to readjust those corresponding clock period. So that's why here this clock constraint I have to, that means there we are, as we are changing the clock period, so that means we are constraining the clock. So that's why here define the clock frequency when you want your circuit to run at. This clock input controls all the timing in the chip or the design. And then again if you might actually recall that we have set the delay, input delay and output delay, that means the rise time and fall time. As we have said for 0.1, so it is basically affecting the overall clock period requirement. Okay. So though we have said that initially we have said that 2 nanosecond, so whenever we have said that rise time of and fall time of 0.1, so at that time it is basically subtracting from the original delay, original clock period. That means that part is basically you need that okay, that is not coming as your original arrival time of the clock. Okay. So like one example, if you take, assume a clock is to be 10 nanosecond, if the output delay is assigned as 5.4 nanosecond, then the input delay would be 10 nanosecond minus 5.4 nanosecond, which is 4.6 nanosecond. Okay. So for this up to this one, for today, up to today's lecture, up to this one. So again in the next lectures we will continue with this static timing analysis. We will see more examples how to calculate the timing information for any circuit, for any design. Okay. So this is it for today. Thank you.